from where you started to where you are right now.
Focus, Shaq.
ChatGPT focus.
You can talk to everything. Okay.
But I know you've done the one.
So the first thing that we need to figure out is the acceleration without the magnet. So what can you measure?
The Eagles being off the
They're not measurable. Gravity, the mass.
You can measure your gravitational force, you can measure your normal force, but so knowing the force parallel, because if your phone doesn't have a good app that measures angles, let me know, we'll bring mine over. So if we measure this angle, what can we find? Force parallel. If you know the mass of the cart, mg, but so you can take this, hang it up, get the weight of the cart, get the mass of the cart.
What about the mass of that?
Mass of what thing?
It's one.
Oh, is it connected to the cart?
Yeah.
Oh! Oh no, you're like moving
Hey,
it.
that's a good question.
Yeah, see, it like moves, so I thought it was.
But it's just pivoted on. So,
Hey, let's
okay, so the first thing you're going to do is measure the angle, get the weight of the cart. Find your force parallel, divide that by the mass, boom, there's your acceleration. Also, have a sync with a garbage disposal. I'm just telling you, have a sync with the garbage disposal. So,
I think she heard you.
you're going to know the mass, you're going to know the force parallel. You can find the theoretical acceleration. Then we want to measure an experimental acceleration without the magnet. So what are some things we can measure?
Time.
Time,
And this.
distance, right?
Find velocity.
No,
Oh my god.
No.
I want to find acceleration.
Our initial velocity, which is 0.
Yep. And we can measure how far it falls.
Distance and
And we know x equals 1/2 at squared plus v naught time.
yeah.
So the v naught time part we don't worry about because initial velocity is 0. So what you want to do, and I tell you in the lab, you want to start where the front of this is at 50 and stop it when the front gets to 10. Okay? No, it doesn't make any difference which 40 centimeters that you use. It just has to be 40 centimeters because that's the length of these plates. Okay? So the next thing you want to do is try and figure out what's going to happen when you put this magnet in here. Now, so, Gavin, can you, Ryan, can you hold this? Just hold that. Got it? Okay. So you want this down about an inch into that plate. So, after you get that time, then you do the same thing, but then you're going to have the magnets in there. So with this one, again, you're going to use the same 40 centimeters. I don't care where the 40 centimeters is, just get 40 centimeters. So you're going to start it like this, have that magnet in there. Now, here's the deal. So this is positioned so that the magnetic field is oriented like this. You're going through here. So here's the main idea, is that let's say, for example, this is, I'm just going to erase it. So let's say you view this as saying, here's a piece of wire. So as that wire enters that magnetic field, let's say this is the north side of the magnetic field. So as that goes through, if this is the north side of the magnetic field, what's Mother Nature going to try and do? So this is the north side. So what is this side seeing?
Well, wait, am I looking at it?
So from the north side, this is the north side of the magnet.
Yeah.
So the magnetic field is going out.
So I'm seeing O's.
So
we're
from
seeing
this
O's.
perspective, you're seeing O's.
Yeah.
So what is it going to try and make?
X's.
It's going to try and make X's. So what can it do to make X's?
I don't know.
I have magnetic. Make a current going.
So it needs to make X's behind it. So the current would go up,
Oh, so that
right?
Yeah.
So that you can make X's in here.
Oh yeah.
So imagine, let me see this. So here's this little segment of the wire. Hey, hold that. So here's what you've got. So imagine you've got the wire. This is the segment of the wire. So the current's going up, okay? Current's going up. But the magnetic field is going out.
Yep, back and back.
So the force is going in the
Left.
And your
opposite
left.
direction, which is why it creates an opposing force.
Oh, yeah.
Okay? So if this is the north side, this thing needs to make X's. The current's going up. The magnetic field is pointing out. That's going to do what?
Slow down.
Slow it down. And you can actually see this. Because when this thing clears that magnet, you can see that thing begin to speed up.
What is the wire that's going to it?
You just assume that it has like an infinite number of wires. So in other words, imagine this is built out of an infinite number of small wires. Okay? Makes sense. So, you're going to do this. You're going to find the force parallel. You're going to find a theoretical acceleration based upon the angle. You're going to calculate an experimental acceleration without it, and then a second one with magnet in it. Toby.
I was gonna say I was confused at the beginning part when you said that we know that it's going out. How do we know that it's going out?
Because I told you that this is the north side of the magnet.
Okay.
It goes from north to south.
So we'll be
So where's
what?
Yeah.
no.
Okay.
Where's the Ferris wheel?
But what the frick is a Ferris
Because of the right hand.
wheel?
So here's how I know that this is how this is pointing. Because if I put this like this, so when I put this like this, this is how I know that that north.
What the?
That's actually kind of funny.
Be careful about that.
Good job, group leader.
Is he gonna like
That could
ski
hit
his
me.
elbow like John Jones?
There we go.
Good job, group leader.
Okay.
Put your hand down. No, I'm saying.
All right. So let's come back up here. Go over a couple of things that are turning loose.